Good morning. Today we're going to be learning how to solve for exponents when we're given exponential graphs and using properties of exponentials. So we already know what an exponential function is. Remember, it's a times b to the n power or a times b to the x power. So now we're actually going to kind of go backwards and solve for that power. So something that's going to be really helpful for us is using the equality of bases property, where it basically just says that the powers with the same positive base other than 1 are equal if and only if the exponents are equal. So basically, this is saying like 5 to the 3 is going to be equal to 5 to the 3 if x and y are different or are the same. So using that, let's go ahead and solve some equations by equating the exponents and using the equality of bases property. So on this one, I have 2/5 times 5 to the x power is equal to 250. So what I'm going to do first is I am going to start to kind of just get it so I only have a base, so then I can really work with it. So in order to get the base by itself, I need to multiply by a, which is 2/5. So remember, if I want to get rid of the 2/5, I have to multiply it by the reciprocal, which is 5/2. So I am timesing 2/5 by 5/2. And I have to do that to both sides. So 2/5 times 5/2, well, that's going to cancel. But 5/2 times 250 is going to give me 625. So then I have 5 to the x power. So 5 to the x is equal to 625. And so what this means by using the equality of bases property is I'm going to try to find a number of base 5 that is 625. So what root of 625 has a base of 5? So if I think about 5s, and 5 times 5 is 25. 25 times 5 is 125. And then 125 times 5 is 625, which is kind of cool because that's to the 4th power. So really what this is saying is if I think about it that way, then 5 to the x power, fingers are fat today, is equal to 5 to the 4th power. And if you're trying to, so since we're trying to solve for x, then 5 to the x is equal to 5 to the 4th, then by the equality of bases property, x has to be 4. These are the same thing, and they are the same base, then x has to be 4. And that is all you do. So you do have to use some math. It's not too crazy. Okay. Let's go ahead and do this one. Again, I want to find out what x is equal to, so I have to get rid of 2 on the left first. So to do that, I'm going to multiply by 1/2 to both sides. Applying 1/2 over here. And then I'm also going to multiply by 1/2 on the other side. Okay. And when I multiply by 1/2 on both sides, stop it. I'm going to get, the 2's cancel. Bada bing. So I'm left with 5/3 to the x. And that's going to be equal to 1/2 times 250 over 27 is going to be 250 over 49. Okay. So now I got to figure out 5 to what power and 3 to what power is going to equal 125 over 49. Well, looking at this, I can actually reduce that fraction, 125 over 49, or sorry, 250 over 49, and I can reduce that by dividing by 2. Yep. By dividing by 2. So then that is also equal to 125 over 27. And the reason why I did this is because now 49, like I know 49 is 7 squared is 49. But I don't necessarily know what 250 is going to be. But then also looking over here, I have to have this equal to a base of 3. So I need to be really thinking about powers of 3. And 49 doesn't really check out. So I'm now need to find what 3 to what power is equal to 5 to what power. So lucky for us, these are easy ones. I know 3 cubed is 27, and then if you check, 5 cubed is also 27. So I can really rewrite this as 5 thirds. Oh my Lord. Dx is equal to 5 thirds to the third power. So we're really kind of working backwards on here. So again, this checks out. 3 to the third power is 27, and 5 to the third power is 125, which is why this checks out. So then finally, our answer has to be x is equal to 3. Okay. And then in this example, we're finally like matching up with the title of our notes. We are trying to find out, we're going to solve by graphing 2 functions. So an animal has 20,000. An animal reserve has 20,000 elk. The population is increasing at a rate of 8% per year, and there is concern that food will be scarce when the population has doubled. How long will it take for the population to reach 40,000? So this is where we're going to really be using a graphing calculator, identifying a function, and trying to figure these bad boys out. So f of x, let's just think about what the population is going to be. Well, we know it starts out with 20,000 elk, and it's increasing at a rate of 8% per year. Since it's increasing, we're going to multiply it by 1.08 each time, right? So thinking about my a value, my a is 20,000, my b is 1.08. So then my equation is simply going to be, since this is an exponential function, is f of x is equal to 20,000 times 1.08. And again, it's 1.08 because we are increasing. If we were decreasing, it would be 0.92 to the x power. Okay. So there we go. That is my function. So then I would graph this function using Desmos, and you can see I did graph this function using Desmos. And then what I want to know is the other thing that I should also graph is what I want, because I want to know how long it will reach for until the population reaches 40,000. So then I would also just graph the equation g of x is equal to 40,000 because I want to find out when it intersects with 40,000. So I did not do this here, but if I were to graph the function g of x equals 40,000, that's a pretty easy function. It's just a horizontal line at 40,000. Oh, I did graph it. Look at me being extra. It's just very faint. So I'm just kind of going over it so you can see it. So then the solution is where they intersect. So I don't really have to go backwards on my exponents. I really just need to look to see where these 2 points intersect. So if I'm looking, they intersect right here, which is at about 9 years. It's a little bit above 9 years, but we're going to round to say it's about 9 years, right? Because the point that they intersect is at 9 years. So at 9 years, the population is about 40,000. So our solution at around 9 years, the population will reach 40,000. What I like about this problem is it really takes what we learned about Module 12, which was a doozy, about modeling of linear equations. Well, now we get a model with exponential functions and find solutions. So identifying solutions to these are the same. We're just really looking again at the point that they intersect, but of course creating that exponential function to graph instead of a linear one.